Matter and change. This is the next unit we're going to dive into. And so we're zooming in now. We're taking a microscopic look at this crazy world we live in. And we're going to start off by talking about the fundamental building blocks of matter. So let's dive in. I suggest that as we go through this, you have a periodic table handy, either open on a tab in your browser that you could toggle over to, or ideally, you could print it off and have it beside you as you go through this lecture. I will post a PDF of a periodic table on Canvas so that you can use it for that. Okay, here we go. Matter and change. Well, what is matter? What is matter? The air we breathe, certainly. The food we eat. The water, beverages we drink. The clothes we wear and the stuff we use. All of those things are matter. In fact, matter is anything that has mass and takes up space. So it's kind of hard sometimes to even think about what isn't matter. Can you think of anything that is not matter? Which of the following is matter? An aardvark, light, energy, all of the above, or none of the above? Let's jump to the exciting conclusion, ladies and gentlemen. The aardvark is the only one of these things which both has mass and takes up space. In fact, everything in this picture that you can see is matter. The rocks, these little bushes, this aardvark's toenails, that's all matter. In fact, some of the stuff you can't see in this picture is matter too. The air that the aardvark is walking through, that has mass and takes up space, as we learned. How about these other options? Light. Does light have mass? No. Does it take up space? It can fill up a room, I suppose, but it doesn't actually take up space. You can't inflate a balloon with light, for example. It doesn't actually take up space. There's never a situation where you can't put another object in a location because light is filling up that space, right? So light does not take up space. Energy. Does energy have mass and take up space? Well, we talked a little bit about how we might be able to say that energy has mass, I suppose. It certainly does not take up space. That is not a form of matter. So almost everything you can think of is matter. But, light, energy, gravity, ideas, all of those things are not matter. Here's a question which you may or may not have learned at some point in your life. Which of the following are the fundamental units of matter? Atoms, molecules, ions, A and B only, or all of the above? And again, for this one, we're just going to jump to the exciting conclusion, because you may not have learned this before. Indeed, atoms, molecules, and ions are the fundamental building blocks of matter. Now, a lot of people, when I give this question, just choose atoms. But it turns out that matter that organizes itself as just purely atoms has different properties than matter that organizes itself as molecules and matter that organizes itself as ions. So some types of matter organize itself just as atoms. Molecules, as we'll learn here in a bit, are one way of atoms kind of bunching together to form new substances. And ions are another way that atoms can bunch together or not to form new substances. An ion is simply an atom that's lost an electron or gained an electron. So it either has a positive or a negative charge. In this particular video, we are going to focus on atoms, and we'll do another video for molecules and ions. So we're going to first just start talking about atoms. So we've seen schematics like this, certainly, in our lives. Over here, this is another representation of an atom. And this is a nice representation, this one right here, because we can certainly see the nucleus, we can see the electron cloud. It's a nice way to visualize an atom. It's important to realize that nobody's ever seen an atom. Atoms are smaller than the wavelength of light that we can see. So nobody has ever seen an atom with their eye. In fact, they've never seen an atom with a microscope. There's not a microscope that can see an atom. Again, because they're just so small that light interacts with them in a different way than light interacts with larger objects. So no one's ever seen an atom. So all we can talk about is ways to represent an atom, because I can't just show you a picture. It doesn't actually exist. So this is one way of representing the atom. Here's another way of representing this atom. And this is a nice representation here. Maybe some of you have seen these in a chemistry class, possibly. These are visualizations of the different energy levels, the different orbitals, where the electrons can live. And as we go through this, we're talking more about atoms. We'll talk about how visualizing the electrons as forming an electron cloud around the nucleus is in some ways a more accurate visualization than visualizing little ping pong balls winging around a nucleus. Indeed, something we'll talk about a little bit more later on in the semester is that when you get down to the microscopic level, almost everything behaves like waves. So you might be picturing the solar system model of the atom, where you've got the nucleus at the center, and then orbiting around there are the electrons. Well, it's not a bad way to visualize the atom, but we find that actually it's incorrect in a number of ways. And it's actually better to visualize the atom as having an electron cloud around them. These electrons are not really, they're not points in space. They're not little tiny ping pong balls. They're not. They act more like waves than they do like little balls. It's crazy. And that's what this visualization here helps us to see. Okay, so what determines the identity of an atom or an element? Well, is it the number of protons, the number of neutrons, or the number of electrons? Good job! It is indeed the number of protons. It's the number of protons that determines the identity of the element. And when we look at the periodic table, we see that the elements are organized according to how many protons they have. The periodic table starts off with hydrogen, and the number 1 here means it has 1 proton. So saying I have hydrogen is the same as saying I have an element with 1 proton. Those are not two different things. We could jump over here. Xenon, one of my personal favorite of all of the elements, and it has an atomic number right here. This is number 54, and that means that there are 54 protons in xenon. So saying I have xenon is exactly the same as saying I have an atom with 54 protons, and saying I have an atom with 54 protons is identical to saying I have xenon. But xenon's way more fun to say. So let's go with that. Now this is interesting. There's only 118 different types of elements, and we think that is in the entire universe, not just in my basement where I am right now. We think that this is in the entire universe, only 118 types of elements. Why do we think that? Well, because you can't have half a proton, right? So we will never ever discover some element that exists on the periodic table in between, just to pick some random ones, manganese and iron. Never, because we can't have 25 and a half protons. So we'll never find an element that fits in here. Will we find more elements at the end? Well, I suppose we could. But we've noticed a pattern, and that is that as the elements get heavier, as we try and pack more and more protons together, they get less and less stable, which makes sense. Recall, protons are positively charged. What do like charges do? Well, they repel. So, when you try and pack more and more protons together, then you get less and less stable. So, the heaviest naturally occurring element is uranium, right here. And we can make, in the lab, we can make heavier elements. Neptunium, plutonium, etc. But you know what? They're very unstable. And though we can create them in the lab, they don't even last that long. They're unstable. They decay into smaller elements almost immediately. So, we think that this 118 is all of them. And really, up here, you get up into these only exist for moments in the lab. They are not useful in any way. I guess we say they exist, because they existed for a moment in some researcher's lab. There's only 92 naturally occurring elements. Okay. Let's zoom in on one of these. We're going to pick carbon. Carbon is 6. Its atomic number is 6, and the symbol we use is C. And so when I say I have carbon, I'm saying I have an element with 6 protons and Likewise, when I say I have an element with 6 protons, I'm saying I have carbon. We call that number the atomic number. Nowhere in the universe is there an atom that has 6 protons and is something other than carbon. The symbol will always start with a capital letter. We can go back here and see that a lot of these have 2 letters, but notice they always start with a capital letter. And then, again, the atomic number is the number of protons. And here we see the atomic weight. The atomic weight is how much an atom of the element weighs. And the units here are a little goofy. It's atomic mass units, which turns out to be a really, really small number of kilograms. It's 10 to the negative 27th kilograms. It's a very small amount of mass. Okay, so for a neutral atom, which of the following is always true? Does the number of protons equal the number of neutrons? Does the number of neutrons equal the number of electrons? Or the number of protons equal the number of electrons? Or does the number of protons plus the number of neutrons equal the number of electrons? Good job! The number of protons equals the number of electrons. Of course, we actually have learned about this, though not in the context of an atom, because we have talked about how electrons are negative, protons are positive, and to have something be neutral, you need equal numbers of positives and negatives. So we must need equal numbers of protons, positive, and electrons, negative, in order to have a neutral atom. Which of the following is a true statement about the mass of a proton, neutron, and electron? Do they all have about the same mass? Choice A. Are protons and neutrons much heavier? Are protons heavier than both neutrons and electrons, or are electrons the heavier ones? Why don't you think about it for a minute and make your choice. Indeed, protons and neutrons are heavier than electrons. Here we have the schematic of an atom, and like I've said, the electron cloud is the area around the outside of the nucleus, and this is where the electrons live. And it contains a very small fraction of the atom's mass, less than 1/2000th. So the electrons, they aren't massless, but they have a mass that's much, much smaller, approximately 2,000 times smaller than the mass of a proton. And in the nucleus, of course, this is where the protons and neutrons live, and the nucleus contains most of the atom's mass. And so here's just a summary. Most of this we've learned before, but not all of it. So protons are positive, electrons are negative, and neutrons are, of course, neutral. And they have about the same mass as a proton. Okay, so we already talked about how this is a really nice picture of an atom because it's easy to visualize. And we talked about how there's a little bit of a problem with the way that the electrons are drawn, because really they act more like waves, matter waves, than they do like little balls, little ping pong balls or little golf balls or something. But again, it's a nice way to visualize that. However, it can be a bit deceiving. Let's look at this question. How much space in an atom is taken up by the nucleus? Is it over 90%, so almost all? About 50%? That would be about what's pictured here. About 1%, so very tiny compared to the overall size. Or less than, well, a tiny, tiny, tiny fraction of the total space. What do you think? Well, I find when I give this question in classes that most students pick this choice or this choice, because I think most people have learned that the nucleus is very small, so a lot of people pick this choice. But it turns out that that's still way overestimating the size of the nucleus. In fact, the nucleus only takes up a few quadrillionths of the total space of an atom. And so, well, this visualization is nice to help us see the atom and kind of talk about the different parts. Indeed, we can have another way of visualizing it. So here's an analogy. This is, of course, Broncos Stadium, the Mile High. And if we were to imagine that the entire atom is Mile High stadium, then we could imagine that the nucleus would be a grain of sand on the 50-yard line, and the electrons would be up in the seats somewhere. So it's crazy to think about. Atoms make up the molecules which make up our bodies, and they're almost entirely empty space. And we're not talking like mostly empty space. Only a few quadrillionths of the atom is actually filled with stuff. The rest is just empty space. So that guy you met at the bar last week, never mind, you didn't go to the bar last week. That guy that you met online last week, he is as vacuous as you thought. Literally. Literally. He's mostly vacuum. Okay. What kind of matter arranges itself as atoms? Well, the noble gases do. The noble gases arrange themselves as atoms. And if you were to look at your periodic table, that column on the far right is all of the noble gases. There we see helium, neon, xenon, krypton, a lot of good ones, radon, argon. All of those are in the noble gas column, that column on the far right side of your periodic table. And those we call them noble gases because they don't form compounds with any other elements. They like to exist all by themselves. So here we see, this is a picture of a neon light, and what is in that tube? Just neon. It's just neon. It's not a compound made of neon. It's just plain old neon. Metals arrange themselves as atoms also. They do form crystalline structures, but they don't form molecules or ions, which are our other two categories of basic building blocks of matter. We can visualize them as being these positive ion cores, and then the electrons form this sort of sea, or almost like a gas of electrons. We talked about how a conductor is something where the electrons are free to move within that conductor, and this is a way of visualizing that. Metals, what makes a metal often is that they are conductors of electricity. Looking back at our periodic table, we find that there's a lot of really interesting organization that happens here in the periodic table. The metals are arranged here on the left side of the periodic table, and the non-metals are arranged here on the right side of the periodic table. And we kind of get this little jaggedy line going down right here, which separates the metals from the non-metals. And we would call those metalloids. Sometimes you'll see them called semi-metals. Notice there is one outlier over here, hydrogen. Hydrogen is a non-metal, though it is over there chilling on the metal side of the periodic table. Something that's super cool about the periodic table is that it was discovered, depending on how you want to look at it, by a man named Mendeleev, and he discovered this in the 1860s. The atom wasn't discovered until 1905, something like that. The electron wasn't discovered until 1899, right? So this man came up with the periodic table based on their physical properties. And what's so interesting about that, and what do I mean by physical properties? Based on their properties that he could measure in 1860. So things like density, color, reactivity, things like that. He organized them based on that, and he came up with this periodic table. It's so amazing to me. And I think what's cool about it is now, as sophisticated 2020 humans, we know that this structure, which Mendeleev came up with, again, using just observations of macroscopic or zoomed out properties, reflects microscopic patterns, which is pretty cool. So get out your periodic table. Let's do some checking here. If an element contains exactly 32 protons, then what do we have? Check out your periodic table. Well, we'd want to be looking for atomic number 32, because 32, the atomic number is how many protons we have. And so if we're looking for atomic 32 protons, then we're looking for atomic number 32, and it is germanium. If the picture below depicts a neutral atom, which atom would it be? This one's a tricky one. This one's tricky. We can tell for sure that it has 3 electrons. We can see for sure that it has 3 electrons. And so now we need to decide, are the red balls in the picture or the black balls the protons? Because I didn't tell you, did I? Well, I know that it's a neutral atom. And so I can see 1, 2, 3 black balls and 4 of the red balls. So the black ones must be the protons because it's neutral. So we need to look for what is the third element, and the third element with atomic number 3 is lithium. It is lithium. If you pick beryllium, you were probably counting the red balls. The trick is that if that was the case, there's only 3 electrons, and so it wouldn't be a neutral atom. It would actually be an ion, and it would be a positively charged ion because I have 1 more proton than I have electron. What are isotopes? Well, maybe you've learned about this in the class. Does an isotope have a different number of neutrons, protons, or electrons? Why don't you think about that for just a second? Well, let's start with this one. Same element with different numbers of protons. That can't even work because the proton is what defines what element we have. So it can't be B. And it turns out that if we change the number of electrons, it is true that we're not changing the element. So we can do that. But it turns out that if we change the number of electrons, then we have created an ion, not an isotope. So an ion is the word for a charged atom that has unequal numbers of electrons and protons. Indeed, I can change the number of neutrons without changing which element I have. We call those isotopes. Okay, so here is a shorthand representation of an atom. Here we see hydrogen. We of course know that hydrogen has 1 proton, and so that's what this means. This means hydrogen has 1 proton. So in a way, that is redundant information. This number right here is the mass number. Now the mass number turns out to be the total number of protons plus the total number of neutrons. And so here we see this is hydrogen. Hydrogen always has 1 proton. Protons plus neutrons is also 1, so there must be no neutrons. So this is a hydrogen atom with no neutrons at all. This right here is a hydrogen atom that has 1 proton, of course. If it's got 1 proton, it is always hydrogen. And it's got 2 things in the nucleus. So if it's got 1 proton, then it must have 1 neutron to make a mass number of 2. Here's carbon. We know that carbon, looking at our periodic table, carbon always has 6 protons. So if the mass number is 12, then it must also have 6 neutrons. Now there's some carbon in the world that doesn't have 6 neutrons. We'll talk more about that in just a second. Now you can simplify this a little bit. Because again, this number right here is the atomic number, and we already know that if we know what the element is. So we can simplify this a little bit. For example, this was hydrogen 1, this is hydrogen 2, and this is carbon 12. We would write this as hydrogen 1, hydrogen 2, and carbon 12. Now be careful. This does not mean hydrogen -1. That would describe an ion, which is a charged atom. This describes hydrogen 1. It's an isotope. And it means that there is 1 subatomic particle in the nucleus. Well, it must be a proton, since hydrogen always has 1 proton. Looking at this one, hydrogen 2, this says it's hydrogen, and there's 2 subatomic particles in the nucleus. Well, hydrogen always has 1 proton, so there must also be 1 neutron. This says carbon 12. It is not carbon -12. That's the key thing here. It is carbon 12. It is its isotope number, and it is not an indication that it is charged. As I mentioned earlier, one place where isotopes sort of show up in our lives is uranium. There's two isotopes of uranium that naturally occur on Earth in any abundance. And that is uranium-238 and uranium-235. Most of the uranium, in fact, over 99% of the uranium on Earth is uranium-238. And you know what? Uranium-238 is not dangerous. You could make a fishing weight out of uranium-238. It would probably work really well. It's actually more dense than lead. It would be a fantastic fishing weight. It would be completely safe, and you could let your 4-year-old play with it. It would be, well, he might swallow it. That would not be safe. But it's not going to be radioactive. Okay. Uranium-235, on the other hand, well, now you can make a bomb out of that. You can power a nuclear reactor out of that. It is unstable. So these are two different isotopes of uranium. And uranium-238 is slightly heavier than uranium-235. And you may hear in the news every now and again, you'll hear about centrifuges as related to nuclear bomb production. It was a real big story, I don't know, 5-6 years ago in Iran, that they had some centrifuges going, and it looked like they were trying to enrich uranium to build a nuclear bomb. And so enriching uranium, what that means is separating out the uranium-235 from the uranium-238. This is what you need to make a bomb. This is what you need to make a fishing weight. How do you do it? With a centrifuge. You spin it really fast, the heavy stuff goes to the outside, the light stuff goes to the inside. Another place where it shows up is in carbon. Now, carbon has 3 naturally occurring isotopes on Earth, and they are carbon-12, carbon-13, or carbon-14. Now notice the atomic weight of carbon is 12.01. Well, how can you have 12.01? You can never have 0.01 of a neutron or 0.01 of a proton. You can't do it. It can't be done. You can only have 1, 2, 3 protons, 4, 5, 6 neutrons. Whole numbers of protons or neutrons. Nobody's ever discovered a half a proton. It doesn't exist. So what does 12.01 mean? It means the average of how much an atom weighs. So any one carbon atom will have a mass of 12, 13, or 14. The average of all of those is 12.01. So, what does that tell you about the relative abundance of the 3 isotopes? Since there are 3 naturally occurring isotopes of carbon, the fact that the atomic weight is 12.01, what does that tell you about their relative abundance? Is there equal amounts of all of them? Is there more carbon-12 than 13 or 14? Is there more 13 than 12 or 14? Or is this a trick question? It's not. Indeed, this says that there is more carbon-12 than carbon-13 or 14. Because it's really close to 12. This is useful to us because humans are able to use this to date things. Because this carbon-12 is stable. However, carbon-14 is not stable. Carbon-14 is being continuously created in the upper atmosphere. When cosmic rays strike the upper atmosphere, they actually interact with nitrogen, and they turn nitrogen-14 into carbon-14. So carbon-14 is being manufactured in the upper atmosphere. However, it's also continually decaying. And both of these processes have been going on at about the same rate since forever, as far back as we know. And so we're continually getting a little bit more production of carbon-14, continually losing a little carbon-14. And so over time, a fixed ratio in the atmosphere of carbon-14 to carbon-12 has existed. And as you and I are alive and breathing, we're constantly taking in this ratio of carbon-12 to carbon-14. And we're eating food that has this ratio of 12 to 14. And we're creating the molecules that make up our bodies that has the ratio of carbon-12 to carbon-14 that basically matches what's in the atmosphere. So we have almost the exact same amount of carbon-14 in our bodies as is in the atmosphere. Same ratio. Once we die, we stop taking in new carbon-14, but it keeps decaying. And so this balance that exists in the atmosphere is upset. The carbon-14 in my body is decaying, and it's not being replaced because those cosmic rays are not getting into my body and reacting with nitrogen in my body. And so if you look at the relative amount of carbon-12 to carbon-14 in my body after I die, then you might be able to tell how long ago I quit adding new carbon-14 to my body. And this works really well for samples up to about 50,000 years old. And so this is an example of a baby mammoth that is almost that old. And so right at the limit of our carbon-14 dating. Now there are other unstable isotopes that also have achieved some sort of long-term balance between creation and decay, and scientists are able to use some of those to make pretty good estimations of dates of things that are older than 50,000 years. But carbon dating is one of the first, carbon was one of the first elements that scientists use to do this type of dating with, and it's very, very effective.